This is Physics 2211, Lab 2, Projectile Motion by Dylan Rudolsky. The purpose of the lab was to record and analyze the motion of a projectile in the lab. We were to throw an object in an arching motion and then account for the drag of gravity in our code. The fundamental physical principles were the position update formula, the velocity update formula, and the formula for drag, which the formula for drag is the drag constant times velocity squared times v hat. Here are the results. You can see the with drag, without drag, and the with drag. This lab shows us that due to the force of gravity and drag, neither the x or y component of the velocity stays constant. The ball eventually starts going down due to gravity, and the drag force slightly decreases its x velocity as it travels. These are the programmed model, not the physical test. The lab setup. For this lab, we just had to find a small projectile that we could weigh and throw. We used a small ball of paper that was wadded up as a projectile. We set up a black background so the tracker application could see the projectile better and put a meter stick as a distance baseline on the ground in front. We then threw the ball up in an arching motion and recorded its trajectory. Here's the video.
You recording? You recording?
The data. The numbers provided by the tracker application and coded simulations were stored into an Excel spreadsheet, and the time and position of the chart and the video are listed in the next slide. These numbers were used in order to calculate the initial velocity of the cart by a simple displacement over time formula. This equated to an instantaneous velocity of 2.97 meters, which was used in the prediction model to predict the movement of the object. The initial position of the object and tracker is just slightly above the origin on the y-axis, slightly below the origin on the y-axis due to slightly inaccurate measurements using the tracker application. Here is the data. Here's the important code. You can see the ball mass of 0.005, the initial velocity, the initial position and velocity vectors, delta t, gravity. Here is the with drag, that was a drag coefficient, and here is without drag, also drag coefficient, 0. As stated, the initial position vector was 0.172, 0 meters, and its initial velocity was 0.927, 2.97, 0 meters per second. Time obviously starts at 0, and delta t is set to 0.032 seconds. The while loop ends at the same length as the length of our video, and Fnet is determined by adding drag force to gravity, which was mentioned before. The rest of the code is just the velocity update formula and the position update formula, which uses the velocity and delta t to calculate the new position at each step. Here's our final trajectories for each thing: the tracker model, the gravity plus drag, and then gravity only. Possible sources of error were misuses of the tracker application when we were deciding on the initial velocities or trying to track the object in general, slight miscalculations regarding the net force due to drag coefficient estimations, and use of improper velocity when coding, as mentioned before. What does it mean? Do any of your models predict a terminal velocity? If the answer is no, what similar experiment could you design to find the terminal velocity of your object? Discuss briefly. My model does not come anywhere near terminal velocity since the object is still accelerating on the way once it hits the ground. Another experiment that could show terminal velocity could be dropping the ball from a much greater height to give it time to accelerate. What if? Imagine the object were initially thrown straight up with the same initial speed as in your experiment. Would the time this object takes to reach the ground floor table be the same, longer, or shorter than the time it took in the original experiment? Discuss briefly and justify your answer with equations, calculations, or computations. It would take the same amount of time as long as the initial speed that it is referring to is only in the y direction. If the y components of the initial velocity are the same, then that means the ball will take the same amount of time to go up because gravity and mass stay the exact same as it will go down. If it is talking about the magnitude of the initial force, or initial velocity, then it will stay in the air for longer because the magnitude, including the y and x components of the initial velocity, will end up being greater than the y component of the initial thing, so the ball will stay in the air for much longer. Thank you.